Good afternoon, everyone. My name is Huang Hongyue. Thanks for being here today. Today's topic is modeling meteorite craters by impacting mutating on sand. As you know, the surface of meteorite is extremely hot because the particles in our atmosphere rub the meteorite. As soon as the meteorite invades the Earth, it also rubs against the rock and grains on the surface of our family, the Earth. Due to this phenomena, we adapted mutating impact on granular bed to simulate this astronomical system. In this presentation, I will show you some obvious features of craters. Next, I'd like to talk about the previous research about impacting on granules. After that, I want to share some experimental results. Lastly, I hope everybody give me some suggestions, then I will very gratitude. Let's go to the feature of craters. Most of craters can be categorized into two parts. One is simple crater, and the other one is complex crater. That is to say, the structure of simple craters is similar to a ball with a smooth surface. It is usually formed by meteorites with lower kinetic energy compared to complex craters. The complex craters almost have obvious features in the middle of the crater. Everyone see this image, this red circle. You must note the central peak in this crater. Scientists developed a mechanism of the formation of this central peak for many years. They declared two probabilities of this formation. One is the bending of the crust. Crust means the skin surface of the celestial body like planets. The other is multi-matter reflow into the bottom of craters. You will see something similar in our experimental result later. Before we discuss our experimental result, I want to introduce some previous research. Scientists have performed many impact experiments in these 20 years. They have used steel balls, water, granule ball as projectiles. The craters formed by different projectiles are very different and spatial. In the steel ball case, you can see the crater with jet eruption. In the water case, strange pattern appear, and something like complex crater has happened in a granular case. But they have one common phenomenon, and that is Pauli law. The diameter of crater and impact kinetic energy, they have a power relationship. For steel balls, this exponent is 0.25, and it will be 0.17 in water. The granule balls case share the same exponent as steel ball. Now, let's go to our experiment. As you see, Figure 1a is our experimental setup, and we construct the phase diagram with two parameters. One is the height of free fall, and the other is the temperature of multitude. We find four phases in our experiment. We call them pearl, cookie, shotgun, snowflake, due to their shape. Next, look at the pearl phase in this diagram. You can obviously find that is two regions. One is at a high height and the other is at a low height. Both of them look like pearl, but their formation is different. In the low height part, mutatin does not expand very wide, so it can gather easily. In the high height part, it should splash out and not come back gather. However, it performs like a pearl. Why? We have one physical argument that high impact energy make the crater deeper, so the slope of the crater side in a cross section will be larger. Then the mutatin is easy to reflow back, and its formation is similar to complex crater. You have a central peak in the middle of the crater. For now, we explain our phase diagram very quickly. Let's see the morphology of craters. Here, lowercase d is the depth of crater. As you see, the depth of crater impacted by multi-team is bigger than steel ball case. We think that is because multi-team can splash and the region can expand, so the projectile does not use more energy to dig the sand out of the crater, then it can dig deeper. But why the depth of crater will decrease quickly and then remain constant? That means the depth is the function of the height, but this function is not a single increasing function. According to this equation, we have one is equal physical argument. We think the granular bed has similar characteristic to non-Newtonian fluid, and that is while you give a large force on non-Newtonian fluid, it will perform like a solid. But if you give a small force slowly, it will look like a fluid. Then we can say that it is because the high height free fall will give the grains large force quickly, then the grains bed will be like a non-Newtonian fluid, and that the depth of the crater remain constant at a high height. Let's see the log-log plot. As you see, it's not a straight line. It's not straight line on log-log plot. So we fit these two regions. And we get two exponents. With low height, we got 0.17, similar to water. And with high height, we got 0.25, similar to steel ball. Now, due to time, let me make a conclusion. We construct a phase diagram of impact kinetic energy versus impact temperature, and it's established and compared with those from using steel ball and liquid drop. We also use many techniques to help us find some detailed information, but due to time, we will not introduce now. If you are interested about this, you can come to physical department and ask me. Okay. We investigate the dynamics of multi-projectile impact on granular media and modify its morphology and that of crater. Lastly, I want to gratitude my teacher Hong Zaiming and Shi Zhouchong. Thanks for his suggestions about measurement. Cai Bingrui and Hao Hong, thanks for their image processing support. Both of them are PhD students in NTHU. Finally, I can't thank Yu Changyi and Wu Yirui either. Thanks for their experimental help. Yu Changyi is a master's student in NTHU. Wu Yirui is a student in Hsinchu High School. This is my presentation. Thank you very much. 如果有任何问题，欢迎跟我说。谢谢大家。